Imagine walking through a park at 2 meters per second. Comfortable pace? Sunday stroll. Now imagine that same speed launching particles 1,000,000 times heavier than comet dust into space. From an object 87% carbon dioxide that should have exploded months ago. But it didn't. 3I Atlas is venting like it has a pressure valve, moving material with precision that natural sublimation simply cannot produce. The December 26th update made it official. The math doesn't work anymore. Scientists can't fit this into any existing category. It's not quite a comet. It's not quite anything. And the more data we collect, the stranger it becomes. Stick around, because by the end, you'll understand why some astronomers have stopped sleeping well at night. Stay with us as this cosmic mystery unfolds, data point by troubling data point. Subscribe now, because 3I Atlas is still making its way toward Jupiter, still breaking every rule we thought we understood, and new observations arrive daily. You'll want to be watching when the full picture crystallizes, and the true nature of what's passing through our solar system becomes undeniable. On December 26, 2024, astronomers released an observational update that should have been routine. Scientists had been tracking 3I Atlas, an interstellar comet, for months. They'd been measuring its dust, analyzing its trajectory, building models to explain what they were seeing. The numbers were slightly unusual, sure, but nothing that screamed impossibility. Until December 26th. That's when the revised estimates came through, and suddenly, the models didn't just fail to fit the data. They broke completely. Let me tell you what changed. The update concerned something technical, something most people would scroll past without a second thought. Dust particle size distributions. Sounds boring, right? Except this revision suggested that the particles being ejected from 3I Atlas weren't the microscopic grains we expect from comets. They were big, dense, heavy. And when I say heavy, I don't mean twice as heavy or even 10 times as heavy. The reports suggested these particles were 6 orders of magnitude heavier than normal comet dust. That's 1,000,000 times heavier. Let that sink in for a moment. 1,000,000 times. Now, before we go further, I need to be honest with you about something. This interpretation isn't universally accepted. There are astronomers who look at this data and see measurement uncertainty. There are scientists who think the particle size estimates are being overinterpreted, that we're reading signals that aren't really there. Science doesn't move in lockstep, and that's a good thing. But even the skeptics will tell you this. Something about 3I Atlas doesn't fit our standard models. The debate isn't whether it's strange. The debate is how strange and why. So what does 6 orders of magnitude actually mean in practical terms? Think about normal comet dust for a second. When a comet approaches the sun, solar radiation heats its surface. Frozen gases sublimate, turning directly from ice to vapor, and that expanding gas carries dust particles along with it. These particles are tiny, typically measured in microns. A micron is 1/1,000,000th of a meter. A human hair is about 70 microns wide. Comet dust grains are smaller than that. They're so light that solar radiation pressure, the actual physical push of sunlight, can shove them away from the sun. That's why comet tails always point away from the sun, regardless of which direction the comet is traveling. The light itself is pushing those particles. But now imagine particles that aren't micron-sized specks. Imagine millimeter-scale aggregates, centimeter-scale chunks, gravel instead of powder. Solar radiation pressure becomes effectively useless at that mass. It's like trying to blow a handful of gravel across the street by exhaling on it. The wind might move dust. It won't move rocks. And if the particles leaving 3I Atlas are really that heavy, then something else has to be accelerating them. Something with enough force to overcome their inertia and launch them into space. Which brings us to the second number that appeared in that December 26th update, the number that made physicists stop and stare at their screens. 2 meters per second. That's the estimated ejection velocity of this material. 2 meters per second. That's walking speed. That's the pace you'd move if you were strolling through a park on a Sunday afternoon. Now, ejection velocities are inferred indirectly. Scientists measure the expansion of the coma, the fuzzy cloud of gas and dust around the comet's nucleus. They use Doppler shifts, subtle changes in the wavelength of light caused by motion. There are uncertainties here, no question. Instruments have limits. Viewing angles matter. But even accounting for those uncertainties, this speed is profoundly strange. Think about what we know happens when a comet sublimates. Frozen gases, locked in ice for billions of years, suddenly turn to vapor as solar radiation heats them. That vapor expands explosively. It doesn't trickle out like water from a leaky faucet. It erupts. The escaping gas can reach velocities of hundreds of meters per second, sometimes over a kilometer per second. It's violent. It's chaotic. It's fast. That's why comets develop those spectacular tails, because the sublimation process is inherently energetic. So when you see an estimate of 2 meters per second, you're looking at something fundamentally different. That's not explosive sublimation. That's slow, steady release. And if the particles are also a million times heavier than they should be, you're not looking at a comet behaving badly. You're looking at something that might not be a comet at all. Scientists started using a phrase in their discussions, carefully, almost reluctantly. Non-impulsive venting. You'll find it in conference presentations, in preprint papers, in informal exchanges between researchers. It's a technical term, but let me translate it for you. Impulsive means sudden and forceful, like an explosion or a burst. Non-impulsive means gradual and controlled. Venting means material is being expelled. So non-impulsive venting means something is releasing material slowly, steadily, without the explosive violence we associate with natural sublimation. It's a phrase that tries very hard to remain neutral, to avoid implications, but you can hear the discomfort in it. You can sense the question nobody wants to ask out loud. Because here's the thing about scientific models. They don't usually break in dramatic, obvious ways. There's rarely a moment where a scientist looks at data and says, well, that's impossible. Instead, models fail quietly. They stop fitting. Parameters drift outside their normal ranges. You start needing more and more special conditions, more coincidences, more fine-tuning to make the observations match the predictions. And at some point, you have to ask yourself, am I explaining the data, or am I explaining it away? By late December, astronomers found themselves in that uncomfortable position. If solar heating is driving this mass loss, why are the particles so heavy? If sublimation is accelerating them, why are they moving so slowly? If this is a normal comet, why does nothing about it look normal? You can propose answers to any one of these questions. Natural phenomena can be weird. The universe is full of edge cases and rare configurations. But when you need special explanations for the mass, special explanations for the velocity, and special explanations for the chemical composition, which we're about to discuss, at some point, you're not describing a rare comet anymore. You're describing something else entirely, and that's where things stood on December 26th. The physics was strange, unsettling even, but it was still physics. Mass was being expelled. Velocities were being measured. Models were being strained, but not shattered. Scientists could still argue about interpretation, about instrument sensitivity, about whether they were seeing signal or noise. But then the spectroscopic data came in, and suddenly the debate wasn't just about motion anymore, it was about composition. It was about chemistry. And that's when things got worse. Spectroscopy is one of those scientific techniques that sounds more complicated than it is. You take light, you split it into its component wavelengths, and you analyze which wavelengths are absorbed or emitted by the material you're studying. Different molecules absorb different wavelengths, so by looking at the spectrum, you can figure out what something is made of. It's essentially cosmic forensics. And when astronomers pointed their spectrographs at 3I Atlas, using both the James Webb Space Telescope and ground-based instruments, they found something they weren't expecting. Carbon dioxide, lots of it. Now, I need to be careful here, because the exact numbers are contested. You'll see claims that 3I Atlas is 87% carbon dioxide by composition. Other scientists will tell you that figure is inflated, that it refers to the relative abundance in the coma, the visible cloud of gas around the nucleus, not the bulk composition of the object itself. These are important distinctions. The coma is the atmosphere, essentially, and what you see in the atmosphere doesn't necessarily reflect what's inside the body. Think of it like analyzing Earth's atmosphere and concluding the planet is mostly nitrogen and oxygen. True for the air, not true for the rock. So when I say 3I Atlas appears to be carbon dioxide dominant, understand that this is model dependent, that it relies on assumptions about how gases are being released and how long they've been accumulating in the coma. But even accounting for those caveats, even being generous with the uncertainties, the carbon dioxide abundance is unusually high. And that's significant because in our experience, in everything we know about comets, water dominates. Water ice is the primary volatile in cometary nuclei. That's not a guess. That's based on decades of observations, missions to comets, chemical analyses of cometary material. Water is the baseline. It's the default. When we think comet, we think dirty snowball, frozen water mixed with dust and trace organics. Carbon dioxide is present, sure, but it's a minor component, not the main event. So why would 3I Atlas be different? Well, there are natural explanations. Carbon dioxide sublimates at lower temperatures than water. If an object forms in an extremely cold environment, farther out in the primordial disk, or in a different stellar system with different thermal conditions, you could end up with a carbon dioxide-rich composition. Interstellar objects, by definition, formed somewhere else, under conditions we can only speculate about. Maybe wherever 3I Atlas came from, carbon dioxide was abundant, and water was scarce. Maybe the chemistry of that system was inverted compared to ours. It's possible. It's not crazy, but it does make 3I Atlas an outlier, and a significant one. The real anomaly, though, isn't just that carbon dioxide is present. It's that carbon dioxide is being released in this sustained, controlled manner, without the object tearing itself apart. Let me explain why that matters. Carbon dioxide ice is less stable than water ice. It sublimates at a lower temperature, which means it starts turning to gas sooner as an object approaches a heat source. And when carbon dioxide sublimates, it does so energetically. The vapor expands rapidly, building pressure beneath the surface. If there's a lot of carbon dioxide in a comet, and if it starts sublimating all at once, the object tends to fragment. It cracks. It breaks apart. Sometimes it explodes outright. We've seen this happen. Comets that undergo catastrophic fragmentation often show signs of carbon dioxide outgassing in the lead-up to their disintegration. But 3I Atlas isn't fragmenting. It's not cracking. It's not shedding large chunks of material or showing signs of structural failure. Instead, it's releasing carbon dioxide steadily, at that slow 2 meters per second pace, while somehow maintaining its integrity. And that suggests something about the internal structure, something about how the gas is being released. Scientists have started talking about regulated release, though they're careful to frame it as a hypothesis, not a conclusion. Regulated means controlled. It means the gas isn't escaping in a chaotic, runaway sublimation process. It means something about the object's structure is throttling the flow, managing the pressure, preventing explosive venting. Think of it this way. Imagine you have a pipe with water under pressure. If the pipe bursts, water explodes out in all directions, chaotic and violent. But if the pipe has a valve, and the valve is partially open, water flows out steadily, controlled, at a rate determined by the valve's setting. Natural sublimation is like the burst pipe. What 3i Atlas seems to be doing is more like the valve. And valves, at least the ones we're familiar with, don't occur naturally. They're designed. They're engineered. Now, I'm not saying 3i Atlas has a valve. I'm saying the behavior resembles regulation, and regulation implies structure, and structure implies constraints that are unusual for natural processes. Let me address the skepticism head on, because it's important. There are scientists who look at all of this and see selection bias. 3i Atlas is unusual, sure, but we've only observed a handful of interstellar objects. Maybe they're all unusual in different ways. Maybe we're just not used to what interstellar comets look like. There are also concerns about instrument sensitivity. Carbon dioxide might appear more abundant than it really is if water's being underestimated due to observational limitations. And there's always the risk of overinterpretation, of seeing patterns in noise, of constructing narratives that sound compelling but rest on shaky foundations. These are valid criticisms. They're part of the scientific process. But they don't erase the fact that 3i Atlas doesn't fit comfortably into any existing category. What we're left with is an object that looks less like a dirty snowball and more like a pressure-managed system. The phrase sounds clinical, almost boring, but the implications are anything but. If you have a system that manages pressure, that regulates gas release, that maintains structural integrity despite ongoing sublimation, you're describing something with internal organization. You're describing complexity. And complexity in nature usually arises from specific processes: geological activity, chemical stratification, maybe tidal forces if there's a companion object we haven't detected. But none of those explanations fit 3i Atlas cleanly. It's not close enough to a star for tidal forces to matter. There's no evidence of a companion. And geological activity requires internal heat, which interstellar objects, cold and isolated for millions of years, shouldn't have. So even if 3i Atlas is natural, and I want to emphasize that it might be, it's not behaving like any comet we've confidently modeled before. It's not just rare. It's categorically different. And that difference, that departure from expectation, is what makes the December 26th update feel less like a data revision and more like a turning point. Because once you start questioning the chemistry, once you start seeing regulated behavior in the mass loss, you can't help but look at the geometry. You can't help but wonder about the structure of the jets, the directionality of the venting, the precision with which material is being expelled. And that's where things get even stranger. Comets have jets. This isn't news. We've known about cometary jets for decades. When a comet's surface heats unevenly, gases sublime from specific locations, creating narrow streams of vapor and dust that shoot out into space. These jets are responsible for much of the visual structure we see in comet tails. They're chaotic, flickering, constantly shifting as the comet rotates and different regions face the sun. But 3i Atlas has jets that don't behave like that. They're directionally stable. They maintain their orientation over time, and they stay narrow in ways that solar wind turbulence shouldn't allow. Let me give you some context. When gas escapes from a comet, it doesn't just flow out into empty space undisturbed. Space isn't empty. There's the solar wind, a stream of charged particles constantly flowing outward from the sun. There's plasma, ionized gas that interacts with the cometary material. There are magnetic fields, pressure gradients, all sorts of forces that disrupt and disperse those jets. What starts as a narrow stream broadens rapidly, spreading out into a fan or a diffuse cloud. The farther the gas travels from the nucleus, the more dispersed it becomes. That's what we see with normal comets. Jets that start narrow and then bloom outward, losing collimation as they interact with the environment. We have excellent examples to compare against. Take 67P/Churyumov-Gerasimenko, the comet that the Rosetta mission studied up close. Rosetta watched that comet's jets for months, watching them flicker on and off, watching them change direction as different parts of the nucleus heated and cooled. The jets were beautiful, dynamic, unpredictable. They erupted from cracks and vents in the surface, sometimes lasting minutes, sometimes hours, but always chaotic, always turbulent. That's what natural sublimation looks like when you see it up close. It's not smooth. It's not orderly. It's a mess. Or consider too I/Borisov, the other interstellar comet we've observed, the one that came through in 2019. Borisov looked like a comet. It had a classical dust fan, a broad tail, predictable behavior. Its jets spread out the way jets are supposed to spread out. Scientists could model it using standard cometary physics, and the models worked. Borisov was weird because it came from outside the solar system, but once you accounted for its interstellar origin, everything else made sense. It followed the rules. 3I Atlas doesn't follow the rules. Its jets appear sustained, maintaining their collimation over distances where they should have broadened significantly. There's limited angular dispersion, meaning the material stays confined to narrow cones rather than spreading out into wide fans. And this happens despite that slow ejection velocity, despite the fact that material is leaving at just 2 meters per second. Slow jets should be even more susceptible to disruption than fast ones. The longer material spends in the solar wind, the more time external forces have to scatter it. But somehow, 3I Atlas is producing jets that stay narrow, that maintain their structure, that look almost engineered. Scientists have proposed a mechanism to explain this, and it's called the vent throat hypothesis. The idea is that beneath the surface of 3I Atlas, there are narrow channels, almost like pipes, that constrain the flow of gas. As gas moves through these channels, it accelerates and cools, and the geometry of the channels shapes the outflow. Think of it like water flowing through a nozzle. The nozzle controls the direction and speed of the water, focusing it into a jet. If 3I Atlas has similar structures, natural fractures, or channels carved by previous sublimation events, those structures could theoretically produce the kind of collimated jets we're seeing. But here's the problem with that explanation. Vent throats require specific geometries. They need to be narrow enough to constrain the flow, but not so narrow that they clog with dust. They need to be oriented in directions that produce stable jets, which means they can't be randomly distributed. And they need to persist over time, which means the surface around them can't be eroding or changing rapidly. All of that is possible, in principle. You can construct scenarios where natural processes create these kinds of structures, but each scenario requires specific conditions, specific histories, specific arrangements of material. You're not describing a generic comet anymore. You're describing a very particular object with a very particular past. And then there's the alternative model, the one scientists are less comfortable discussing, but can't entirely dismiss. Porous sublimation. The idea here is that instead of gas erupting from discrete vents, it's percolating up through a porous structure, like water seeping through sand. As the gas moves through the pores, it aggregates into larger flows, and those flows emerge from the surface in organized patterns. This model can explain sustained jets, but it also requires a very specific kind of porosity. Too much porosity, and the gas disperses before it reaches the surface. Too little, and pressure builds until the object fractures. You need just the right balance, just the right structure, for this to work. And once again, you're invoking special conditions, fine-tuned parameters, things that nature can produce but rarely does. Why does geometry matter more than speed? Because geometry implies control by structure. Speed can vary. Sublimation can be fast or slow depending on temperature, composition, distance from the sun. But geometry, the shape and direction of the jets, is dictated by the internal architecture of the object. If the jets are narrow and stable, something about the interior is causing that. Something about the way material is stored and released is producing order rather than chaos. And order, in nature, tends to arise from processes that organize matter: crystallization, sedimentation, maybe biological activity if we're talking about Earth. But for an interstellar object, for something that's been drifting through the void for millions of years, the explanations become strained. Now, there are counter-arguments. Maybe what we're interpreting as sustained jets are actually projection effects, artifacts of our viewing angle. If we're looking at 3i Atlas edge-on, we might see structure that isn't really there, patterns created by our perspective, rather than the object itself. Or maybe the temporal sampling is too sparse. We're not watching this object continuously. We're taking snapshots, separated by hours or days. Maybe the jets are changing, fragmenting, behaving chaotically, and we're just missing it because we're not looking often enough. These are reasonable objections. They remind us that our data is incomplete, that our observations are limited, that we might be constructing narratives from insufficient evidence. But even accounting for those objections, even being cautious about over-interpretation, the jets of 3i Atlas remain anomalous. They don't look like what we expect from chaotic sublimation. They look organized. They look directed. And if mass is leaving this cleanly, if material is being expelled along narrow, stable trajectories at walking speed, we have to ask the next question. The question that leads us into even stranger territory. If mass is leaving the object, where is the reaction force? Where is the momentum being transferred? Because every action has an equal and opposite reaction, and if 3i Atlas is shedding mass, that mass should be pushing back. It should be accelerating the object in the opposite direction, and as far as anyone can tell, it's not. Let me explain something fundamental about how comets move. When a comet releases gas and dust, that ejected material carries momentum. Momentum is mass times velocity, and if you're throwing mass in one direction, you experience a force in the opposite direction. This is Newton's third law, one of the most basic principles in physics. Rockets work this way. Jet engines work this way. Comets work this way. When gas erupts from a comet's surface, the comet recoils, just slightly, in the opposite direction. Over time, these recoils add up. They alter the comet's trajectory, causing it to deviate from a purely gravitational orbit. Astronomers call these deviations non-gravitational accelerations, and they're expected. They're part of the standard model. Every active comet we've studied shows them, except 3i Atlas. Astronomers have been tracking its orbit carefully, comparing its actual position to where it should be based on gravitational forces alone, and they're not seeing clear evidence of non-gravitational acceleration. Now, I need to be precise here. The absence of evidence isn't evidence of absence. 3i Atlas is far away. The measurements are difficult. The uncertainties are large. It's possible that non-gravitational accelerations are present, but too small to detect given current observational limits. But it's also possible that they're genuinely absent, or much smaller than they should be given the amount of mass being lost. And that's deeply strange. Think about what the observations are telling us. 3i Atlas is shedding material. We can see the coma. We can measure the mass loss rate. Scientists estimate it's losing somewhere in the range of tens to hundreds of kilograms per second. That's not trivial. That's a lot of mass. And if that mass is being ejected at 2 meters per second, even that relatively slow speed carries momentum. The object should be experiencing a measurable recoil. Its trajectory should be bending, even if only slightly. But the trajectory appears consistent with gravity alone, or close enough to it that deviations are hard to confirm. Where should this momentum appear? In trajectory deviations, first and foremost. If 3i Atlas is venting in a preferential direction, like from a single hemisphere or a dominant jet, the object should be accelerating in the opposite direction. We should see its orbit shift, its velocity change, its path deviate from the predictions. We should also potentially see spin state changes. If jets are erupting asymmetrically, they can exert torque, causing the object to spin up or spin down. This happens with comets all the time. But again, for 3I Atlas, these signatures are either absent or below detection thresholds. Now, let's talk about the uncertainties, because they're significant. 3I Atlas is an interstellar object. It's not passing close to Earth. We're observing it from a distance, trying to measure tiny accelerations against the enormous gravitational pull of the Sun. The viewing geometry matters too. If we're looking at the object from an angle where the jets are aligned with our line of sight, we might not see lateral accelerations. And there's always measurement noise, instrument limitations, the fact that astrometry, the science of measuring positions, is hard. All of these factors mean we have to be cautious. We can't say definitively that non-gravitational accelerations are absent. We can only say they're not clearly detected. But let's assume for a moment that the observations are real, that the lack of clear trajectory deviation is telling us something genuine about 3I Atlas. If that's the case, we need an explanation. We need a mechanism that allows mass loss without significant momentum transfer. And scientists have proposed several exotic natural explanations. One is clathrate-mediated release. Clathrates are structures where gas molecules are trapped inside cages of water ice. If gas is being released from clathrates rather than from direct sublimation, the process might be slower and more evenly distributed across the surface, potentially canceling out directional accelerations. It's an elegant idea, but it requires clathrates to be the dominant form of volatile storage, which is unusual. Another explanation is electrostatic lofting. This is the idea that dust particles become electrically charged and are lifted off the surface by electrostatic forces rather than by gas pressure. If that's happening, the momentum might be transferred differently, perhaps spread out over a larger area, or canceled by opposing charge distributions. But electrostatic lofting typically works for small particles, not the millimeter to centimeter scale aggregates that 3I Atlas seems to be ejecting. Scaling this mechanism up to explain heavy particle ejection is difficult. A third possibility is aggregate breakup with canceling vectors. Maybe material is being ejected in multiple directions simultaneously, and the momentum vectors cancel out. If jets are firing from opposite sides of the object with similar strength, the net acceleration could be close to zero. But this requires a very specific symmetry, a very specific distribution of active regions. And it needs to be sustained over time, because 3I Atlas has been shedding mass for months. Maintaining that symmetry, maintaining that balance, over rotation periods, and changing solar illumination is a lot to ask of random processes. Each of these explanations requires fine timing, specific geometry, narrow parameter windows. None of them are impossible. Nature can be surprising, but they're also contrived. They're the kinds of explanations you propose when the simple models don't work, when you need to add complexity to save the hypothesis. And at some point, you have to ask yourself, am I adding complexity because the data demands it? Or am I adding complexity because I'm uncomfortable with the alternative? There's a philosophical tension here, one that scientists grapple with constantly. When does rare become special pleading? When does unusual become implausible? We know that nature produces edge cases, objects that sit at the extremes of parameter space. But those edge cases still follow the laws of physics. They still obey conservation of momentum. They still behave in ways that, even if surprising, are ultimately explainable. 3I Atlas seems to be testing that assumption. It seems to be showing us behavior that requires ever more specific conditions, ever more finely tuned coincidences to explain naturally. And that's unsettling. Not because it proves anything. It doesn't. But because it raises the possibility that our assumptions are incomplete. Maybe there are processes we don't understand. Maybe interstellar objects behave in ways we haven't accounted for. Or maybe, just maybe, Three-Eye Atlas isn't entirely natural. That thought sits in the back of every astronomer's mind, unspoken but present. Because there's a precedent for this. There's another interstellar object that caused similar debates, similar discomfort, similar questions. And ignoring that comparison, pretending it doesn't exist, would be dishonest. So let's talk about Oumuamua. In October 2017, astronomers discovered an object moving through the inner solar system at high speed. It had come from outside, entering from interstellar space, and it was leaving just as quickly. They named it Oumuamua, a Hawaiian word meaning scout or messenger. At first, they thought it was a comet. Then, they thought it was an asteroid. Then, they realized it was neither, or both, or something in between. Oumuamua was strange. It was elongated, tumbling, non-reflective, and most famously, it accelerated as it left the solar system, exhibiting a non-gravitational force that couldn't easily be explained by outgassing, because no outgassing was detected. The scientific community debated Oumuamua intensely. Some researchers proposed it was a fragment of a larger body, maybe a shard of a shattered planet. Others suggested it was a hydrogen iceberg, an exotic object made of frozen hydrogen. One prominent astronomer, Avi Loeb, suggested it might be artificial, a light sail or probe sent by an extraterrestrial civilization. That suggestion was controversial, to put it mildly. Most scientists rejected it, not because it was impossible, but because extraordinary claims require extraordinary evidence, and the data on Oumuamua was sparse. By the time anyone realized how unusual it had already left the solar system, beyond the reach of our telescopes. The Oumuamua controversy had a lasting effect on the astronomical community. It made scientists cautious. It made them wary of speculation. No one wanted to be the next person claiming an interstellar object might be artificial, only to be proven wrong or ridiculed. The memory of that debate, the reputational costs, the public attention, it all created an incentive to be conservative, to interpret data in the most mundane terms possible, to avoid jumping to conclusions. And that caution, that institutional memory, is shaping how scientists talk about Three-Eye Atlas. But let's be clear about the similarities. Both Oumuamua and Three-Eye Atlas are interstellar objects. Both exhibit non-standard behavior that doesn't fit comfortably into existing categories. Both have caused models to fail or require significant adjustment. Both have sparked debates about whether our assumptions are correct. The difference is that Three-Eye Atlas shows visible mass loss. We can see the coma. We can measure the outgassing. We have spectroscopic data, particle size estimates, ejection velocities. The data quality is better. The observational coverage is more complete. We're not working from a handful of images taken as the object was leaving. We're tracking Three-Eye Atlas in real time. And yet, despite the better data, or perhaps because of it, Three-Eye Atlas is in some ways more puzzling than Oumuamua. Oumuamua's acceleration could be explained, awkwardly, by invoking unseen outgassing. The absence of a visible coma was strange, but maybe the gas was transparent. Maybe it was hydrogen. Maybe we just missed it. With Three-Eye Atlas, we can't use that excuse. We can see the mass loss. We can measure it. And the measurements don't make sense. The particles are too heavy. The speed is too slow. The chemistry is inverted. The jets are too stable. And the momentum accounting doesn't balance. Every attempt to fit this object into our existing framework requires adding exceptions, special conditions, improbable coincidences. So maybe the problem isn't with the object. Maybe the problem is with the framework. Maybe our taxonomy is incomplete. We classify objects as comets or asteroids based on whether they show comae, whether they have tails, whether they outgas. But what if there's a third category? What if there are objects that don't fit neatly into either box? Natural objects, perhaps, but shaped by processes we haven't witnessed, formed under conditions we don't fully understand. Or maybe not entirely natural. Maybe relics. maybe engineered debris, maybe the remnants of something that once had a purpose but no longer functions. This is where the conversation becomes uncomfortable, where scientists stop publishing and start whispering. Because once you start entertaining the possibility that an object might be artificial, you're stepping outside the boundaries of conventional astronomy. You're entering territory where evidence is thin and speculation runs wild. And no one wants to be the person who cried alien. But avoiding the question doesn't make it go away. If 3I Atlas isn't a comet, if it doesn't fit any natural category we recognize, we owe it to ourselves to ask, what else could it be? I'm not saying it's a spacecraft. I'm not saying it's a probe. I'm saying that our current categories might be insufficient, that the universe might contain objects we haven't accounted for, that intelligence, if it exists elsewhere, might leave traces that don't look like radio signals or megastructures. Maybe they look like slow, venting objects drifting through interstellar space. Maybe they look like 3I Atlas. Or maybe not. Maybe the natural explanation is correct, and we just need more data, better models, a deeper understanding of cometary physics. Maybe 3I Atlas will eventually be explained, and future textbooks will describe it as an unusual but entirely comprehensible object. But until then, until we have that explanation, the comparisons to Oumuamua will persist. The questions will linger, and the possibility, however remote, that we're looking at something genuinely unprecedented will hang over every observation, every measurement, every attempt to make sense of what we're seeing. Because the truth is, we don't know, and maybe that's the most important thing to admit. We don't know what 3I Atlas is. We don't know if our models will eventually accommodate it or if they'll break entirely. We don't know if this is the beginning of a new field of study or just an anomaly that will fade into obscurity. What we do know is that the universe is stranger than we imagined, that objects exist which challenge our assumptions, and that maybe, just maybe, we need to expand our thinking about what's possible. 3I Atlas isn't happening in isolation. Over the past few years, scientists have been encountering anomalies across multiple fields, situations where models fail, where data doesn't fit, where artificial intelligence systems discover patterns that human intuition missed. It's becoming a theme, almost a motif. The idea that our understanding of physics, as comprehensive as it seems, might have blind spots, gaps, regions where the rules we've written down don't quite capture what's really happening. Take fluid dynamics. For over a century, scientists have been studying how fluids flow, how turbulence develops, how vortices form and dissipate. We have equations, the Navier-Stokes equations, that describe fluid behavior. These equations work. They power weather prediction, aircraft design, pipeline engineering, but they're also incomplete. There are solutions to these equations that we can't find analytically. Regimes where turbulence becomes so complex that even supercomputers struggle to simulate it accurately. And recently, AI systems trained on experimental data have started finding solutions that human physicists didn't predict. Flow patterns that emerge under specific conditions, but that our intuition said shouldn't exist. Or consider plasma turbulence. Plasmas are ionized gases, the fourth state of matter, and they're everywhere in the universe. Stars are made of plasma. The solar wind is plasma. Fusion reactors contain plasma. Understanding how plasma behaves is crucial for astrophysics and energy production. But plasma turbulence is notoriously difficult to model. The interactions between charged particles, magnetic fields, and electromagnetic waves create cascades of complexity that resist simple description. Scientists have been working on this for decades, and progress has been slow. Then AI came along. Machine learning systems, trained on observational data and simulations, began identifying patterns in plasma behavior that conventional models missed, instabilities that shouldn't occur, energy transfers that violated expectations, structures that persisted longer than they should. Why does this matter? Because it suggests that physics, as we understand it, is increasingly reliant on pattern recognition rather than first principles. We're moving away from the idea that a few elegant equations can describe everything, and toward a model where complexity emerges from interactions we can observe, but not fully explain. And that shift, that transition from determinism to data-driven discovery, is both exciting and unsettling. It means we're finding answers, but it also means we don't always understand why those answers work. There's a parallel here with 3i Atlas. Human intuition says the object's behavior is impossible. Heavy particles can't be ejected slowly without more energy. Carbon dioxide dominance should lead to fragmentation. Stable jets shouldn't form without structural control. Our models, built on decades of cometary observations, tell us this shouldn't happen, but the data says it is happening. The observations are there. The measurements, imperfect as they are, point to something real. So either the data is wrong, which is always possible, or our intuition is incomplete. And increasingly, across multiple fields, it's the intuition that's failing. This raises a deeper question. Are anomalies becoming normal? Are we entering an era where the exceptions outnumber the rules? Where the universe reveals itself to be more diverse, more strange, more full of edge cases than we ever anticipated? Or are we just getting better at detecting things we used to miss, pulling back the curtain on complexity that was always there? I don't have an answer, but I think it's worth noting that every time a new instrument comes online, every time we extend our reach into new wavelengths or higher resolutions, we find things that don't fit, objects that defy categorization, phenomena that require new physics, or at least new applications of old physics. And maybe that's the lesson of 3i Atlas. Not that it's artificial, though it might be. Not that it's natural, though it probably is. But that it represents a class of objects we didn't know existed. A category we haven't named yet. Something that sits in the gap between comet and asteroid, between natural and designed, between expected and impossible. Maybe our failure isn't in the data. Maybe our failure is in the taxonomy. Maybe we've been trying to fit the universe into boxes it was never meant to occupy. There's another implication too, one that connects to the broader theme of AI-driven discovery. If intelligence exists elsewhere in the universe, if there are civilizations older than ours, more advanced, more capable, why would they build things that shout their presence? Why would they construct megastructures, send powerful radio signals, make themselves obvious? Maybe they wouldn't. Maybe intelligence, especially intelligence that survived for millions of years, learns to be subtle. Maybe it builds systems that blend in, that look almost natural, that operate on timescales and energy scales we're only just beginning to measure. Maybe the galaxy is full of these things, and we've been walking past them for decades because we didn't know what to look for. Or maybe not. Maybe I'm projecting patterns where none exist, seeing purpose in randomness. That's the risk of speculation. But here's the thing. Someone has to ask these questions. Someone has to look at 3i Atlas and wonder if it's more than just a comet. Because if it is, if even one object out there is genuinely artificial or shaped by intelligence, the implications are staggering. It means we're not alone. It means the universe contains complexity beyond natural processes. It means everything changes. And if it's not, if 3i Atlas is eventually explained, fit into a revised model of cometary behavior, classified as unusual but natural, then we still learn something. We learn that the universe is weirder than we thought, that our models need updating. That interstellar space produces objects we didn't anticipate. Either outcome is valuable. Either outcome expands our understanding, but only if we're willing to ask the uncomfortable questions. Only if we're willing to look at the data without prejudice and say, I don't know what this is. Because that's where we are with 3i Atlas. We don't know. And that uncertainty, that gap in our knowledge, is where discovery happens. It's where science moves forward, not by confirming what we already believe, but by encountering things that don't fit and having the courage to investigate them honestly. So whether 3i Atlas is a comet, a relic, or something entirely different, it's already succeeded in one thing. It's made us question our assumptions, and that, more than any specific answer, is what matters. Let me ask you something. What if the real question isn't whether 3i Atlas is artificial or natural? What if the real question is, why are we so invested in that binary? Why do we need it to be one or the other? Why can't it be something in between? Something that defies easy categorization. Something that forces us to rethink what those words even mean. We live in a universe that's been around for 13.8 billion years. The sun formed 4.6 billion years ago. Life on Earth appeared roughly 3.7 billion years ago. Modern humans have existed for maybe 300,000 years. Recorded history spans about 5,000 years. The entire span of human observation, from the first person who looked up at the stars and wondered what they were to the telescopes we use today, covers a blink. A fraction of a percent of cosmic time. And in that blink, we've developed models, built frameworks, created taxonomies that we now treat as if they're universal truths. But they're not. They're provisional. They're the best we can do with limited data. And when that data changes, when objects like 3i Atlas show us behavior we didn't predict, maybe the problem isn't with the object. Maybe the problem is with our categories. So let's reframe the question. If 3i Atlas is natural, what unknown astrophysical processes exist? What conditions in interstellar space, or in the stellar systems where these objects form, could produce something that vents carbon dioxide at walking speed while maintaining structural integrity? What chemical environments, what thermal histories, what long-term evolutionary pathways could lead to an object that looks like this? Because if nature can make 3i Atlas, then nature is more creative than we've given it credit for. And that's exciting. That means there are entire classes of phenomena we haven't discovered yet. Processes that operate on scales or timelines we don't typically study. It means the universe is richer, more complex, more full of surprises than our textbooks suggest. But if 3i Atlas isn't natural, if it's artificial, or at least influenced by intelligence, then we have to ask an even stranger question. Why? Why would something designed, something built, behave this way? Why passive? Why slow? Why drift through interstellar space, venting gas at 2 meters per second? If you're going to build a spacecraft or a probe, why not make it fast? Why not give it obvious propulsion, clear intent? Why let it wander for millions of years, slowly shedding material, looking for all the world like a comet that's just slightly off? Maybe because that's the point. Maybe the goal isn't to be noticed. Maybe the goal is to blend in, to move through space in ways that don't attract attention, to observe or collect data or perform some function we can't imagine without announcing itself. Or maybe 3i Atlas isn't a functional object at all. Maybe it's a relic, a piece of abandoned infrastructure, something built long ago for a purpose that's no longer relevant, now drifting through the galaxy like space junk. We have plenty of junk in Earth orbit, satellites that stopped working decades ago but still circle the planet. Scale that up. Imagine a civilization millions of years old. How much debris would they leave behind? How many objects would they build and then forget, letting them drift into interstellar space where they could wander for eons? Or maybe it's something even stranger. Maybe it's archaeological. Maybe 3i Atlas is the remnant of a long-dead system, a piece of technology so old that whatever made it is gone. Imagine finding an ancient artifact on Earth, something from a civilization that vanished 10,000 years ago. You could study it, analyze it, try to understand what it was for, but you'd never hear an explanation from its creators. 3i Atlas might be like that. A message from the past. Not a radio signal, but an object. Something physical. Something real. Drifting through space until we happen to notice it. I'm speculating. I know that. But speculation is what we do when we don't have answers. And right now, we don't have answers. We have data that doesn't fit. We have models that break. We have an object that behaves in ways no comet should, and no amount of tweaking parameters or invoking rare conditions has made it fit comfortably into our understanding. So maybe it's time to expand that understanding. Maybe it's time to admit that the universe might contain things we haven't accounted for. Natural things, artificial things, or things that blur the line between the two. Here's what I think is important. Whether 3i Atlas is a comet, or a relic, or something else entirely, it's shown us the limits of our knowledge. It's revealed gaps in our models. It's forced us to confront the fact that we don't understand everything, that the cosmos is bigger and stranger than our equations suggest. And that's valuable. That's progress. Because science doesn't advance by confirming what we already believe. It advances by finding things that don't fit and asking why. And maybe, just maybe, 3i Atlas is the first of many. Maybe interstellar space is full of objects like this, drifting between the stars, too slow to be noticed, too subtle to scream. Maybe the galaxy is filled with artifacts, natural or otherwise, that we've been missing because we didn't know what to look for. Maybe every stellar system produces a few of these, and they wander for millions of years, occasionally passing through other systems, occasionally being detected by civilizations curious enough to watch. Or maybe 3i Atlas is unique. Maybe it's a one-time fluke, an edge case that will never be repeated. But we won't know unless we keep looking. Unless we build better instruments, collect more data, and remain open to the possibility that the universe is weirder than we thought. So what's the real question? It's not whether 3i Atlas is artificial. It's not whether it's natural. The real question is, what does it mean that we found it? What does it say about the universe that an object like this exists, whether designed or not? What does it say about our place in the cosmos that we're capable of detecting something this subtle, this strange, this borderline impossible? Because a century ago, we couldn't have seen 3i Atlas. We didn't have the telescopes, the spectroscopy, the computational power to analyze what we were looking at. But now we do. And the more we look, the more we find things that challenge us, that push the boundaries of what we think is possible. Maybe 3i Atlas is not proof of intelligence. Maybe it's proof of ignorance. Proof that for all our progress, for all our understanding, we're still just beginning to grasp what's out there. We're still learning the rules. We're still discovering the categories. And every time we find something that doesn't fit, every time an object comes along that breaks our models and forces us to rethink our assumptions, we get a little bit closer to understanding the universe as it actually is, not as we wish it to be. And maybe that's the point. Maybe the universe doesn't care about our categories. Maybe it doesn't care whether we call something natural or artificial, comet or relic, expected or impossible. Maybe it just is, in all its complexity, and we're the ones trying to make sense of it. And sometimes we succeed. We build models that work, theories that predict, frameworks that explain. But sometimes we fail. We encounter 3i Atlas. We see data that doesn't make sense. And we have to sit with that discomfort, that uncertainty, and admit that we don't have all the answers. Because here's the truth. The universe may not scream. It may not announce itself with megastructures or radio signals or obvious signs of intelligence. It may leak quietly, at walking speed, venting carbon dioxide from an object that looks almost like a comet, but isn't quite. It may whisper rather than shout. And if we're not listening, if we're not paying attention, if we're too committed to our existing models to notice when something doesn't fit, we'll miss it. We'll walk right past it, convinced we understand, never realizing that the thing we dismissed as a comet was actually the most important discovery of our lifetime. So I'll leave you with this. 3I Atlas is still out there, still venting, still moving through space at its slow, deliberate pace. Scientists are still watching it, still collecting data, still trying to make sense of what they're seeing. And maybe one day, they'll have an answer. Maybe they'll publish a paper that explains everything, that fits the object neatly into a revised model of cometary behavior, that makes all the strangeness disappear. Or maybe they won't. Maybe 3I Atlas will remain an anomaly, a mystery, a reminder that the universe is bigger than our understanding. Either way, it's changed something. It's shown us that the cosmos contains surprises, that the space between stars isn't empty, and that maybe, just maybe, we're not looking hard enough.